Welcome to the learning module of Nirmala College for Women, Coimbatore. I am Ms. J. Antonette Luciana Sherryn, Assistant Professor from the Department of Chemistry. In this video, we will be studying about isomerism in the coordination compounds. The list of the contents in this video are coordination compounds, isomerism in coordination compounds, flowchart of isomerism, structural isomerism, and stereoisomerism. Coordination compounds. What are actually coordination compounds? A coordination compound or a complex consists of a central metal atom or an ion called the coordination center and surrounding array of bound molecules or ions that are known as ligands or complexing agents. Many metals, especially those of the transition metals or D block elements, are called as the coordination complexes. The central atom, together with all the ligands, comprise the coordination sphere. The central metal atom or the ion and the donor atoms comprise the first coordination sphere. Coordination refers to the coordinate covalent bonds between the central metal atom and the ligands. The atom within the ligand that is bonded to the central metal atom is called as the donor atom. And the number of donor atoms which is attached to the central metal atom is called as the coordination number. Moving on to the second point, isomerism in coordination compounds. What is isomerism? The coordination compounds which are having the same molecular formula but the ligands attached to central metal atom in different ways are called as the isomers. These isomers have different property and the phenomena is called as isomerism. Coming to the flowchart of isomerism. The molecules which are having the same molecular formula and if it is going to have are the bonds between the central metal atom and the ligands are with the same atoms. If yes, the answer is going to be the enantiomers and diastereomers, and if the answer is no, it is going to be consisting of 5 different classifications called the ionization isomerism, linkage isomerism, coordination isomerism, hydrate isomerism, and polymerization isomerism. It can be subjected into 2 different major classifications called the stereo or the configurational isomers or the structural or constitutional isomers. So this particular slide shows the major classification of the isomers. Structural isomerism. Structural isomerism is nothing but the phenomena in which the compounds with the same molecular formula but the attachment of the ligand with the central metal atom is different. Structural isomerism is different from stereoisomerisms in terms of the spatial arrangements of the atoms. Ionization isomerism. Compounds with the same formula but which give different ions in solution exhibit ionization isomerism. The difference is in which ion is included as the ligand and which is present to balance the overall charge. For example, pentamine chlorido-cobalt bromide exhibits 2 different isomers in which The first case, the chlorine is present inside the coordination sphere, and in the second case, chlorine is present outside the coordination sphere to balance the overall charge. So this particular isomerism is called as the ionization isomerism, and some other examples are also given here, which includes the complexes of platinum and complexes of cobalt. Linkage or ambidentate isomerism. Some ligands can bond to the metal through different atoms. When an ambidentate ligand having two different donor atoms coordinates to the metal through either of its donor atoms, two different complex compounds are obtained. These are different because they have different structures. The most common examples are thiocyanate, isothiocyanate, nitrite, nitrito, etc. The class A metal ions, or the hard acids, they tend to bond to the nitrogen of the thiocyanate, whereas the class B metal ions, or the soft acids, bond through the sulfur through the isothiocyanate. But the differences are small, and the solvent used in the complex influences the bonding. Here are some of the examples of ambidentate ligands, which in turn produces ambidentate isomerism. They are nitro, nitrito, cyano, isocyano, cyanato, isocyanato, thiocyanato, and isothiocyanato. Coordination isomerism. Coordination isomerism occurs in compounds containing the complex anionic and cationic parts, which can be viewed as an interchange of some of the ligands from the cation to the anion. Hence, there are two complex compounds bound together, one with a negative charge and the other with a positive charge. In coordination isomers, the anion and the cation complexes are exchanging one or more ligands. So here is an example of tetramine zinc 2 tetrachlorocuprate, which is exchanging the zinc and the copper metals in solution. The other examples are hexacyanochromium, hexamine cobalt, which is exchanging the chromium and the cobalt metal atom. Here, the ammonia and the cyanide ligands exchange the positions and the isomers are formed. Hydrate isomerism, as the name suggests, involves the H2O molecules, in which it is replaced by the anions present outside the coordination sphere. The standard example is trichlorochromium hexahydrate, which can have three distinct crystalline compounds, which are violet, blue-green, and dark green in color. The action of silver nitrate solution on these isomers indicates that they have 3, 2, and 1 Cl- ions or chloride ions respectively outside the coordination sphere. This is another example for the hydrate isomerism, which involves the H2O molecules which is being replaced by the ions present outside the coordination sphere. Polymerization isomerism. This type of isomerism is found in those complex compounds whose formulae appear to be the polymers of some simple complex compound. These complex compounds have the same ratio of different metal atoms and ligands in them. Here are some examples of the complexes containing platinum and cobalt. Coming to the fifth part, the stereoisomerism. Stereoisomerism. This arises when the molecules with the same chemical formula and same attachment with the atoms or same coordination with the ligands to the metals compared to each other, but different spatial arrangement of the atoms or the ligands in the space. And such molecules are called as the stereoisomer, and the phenomena is known as the stereoisomerism. It is classified into two different classifications called as the geometrical isomerism and the optical isomerism. The geometrical isomerism arises where the complex compounds have the same ligands in the coordination sphere, but the relative position of the ligands around the central metal atom is different. So we will be seeing the geometrical isomerism in two different geometries where it is a 4 coordinated complex compound and 6 coordinated complex compound. In a 4 coordinated complex compound, the central metal atom may have either a tetrahedral or a square planar geometry. The geometrical isomerism cannot be shown by tetrahedral complexes because all the 4 ligands in this geometry have adjacent positions to one another and all the 4 bond angles are same, which is nothing but 109.5 degree. Geometrical isomerism in square planar complexes. A square planar complex having similar ligands at adjacent positions, that is 900 apart, is called as the cis isomer, while a square planar complex having two similar ligands at positions opposite, which is 1800 apart, is called as the trans isomer. The cis and the trans isomer of the square planar complexes are common, with the platinum 2 complex being one of the most common metal ions which is studied. The examples are shown below. Geometrical isomerism in a 6 coordination complex, which is nothing but the octahedral complexes. We know that the complex compound have a central metal atom with a coordination number which is equal to 6 is called octahedral in shape. So MA4B2 type complexes where A and B are monodentate ligands may have two isomeric forms called as the cis and the trans. Important examples of octahedral complexes of this type are tetramine chlorido-cobalt and tetramine nitrido-cobalt. In this cis isomer, two Cl- ions occupy the adjacent positions of the octahedron, while in trans isomer position, these ions have opposite positions. And here is the example. In the other case where Ma3B3 type complexes, they have two isomeric forms called as the FAC and MER, which is nothing but the facial and the meridional complexes. The facial isomers have three identical ligands on one triangular face isomers and have three identical ligands in a plane bisecting the molecule. Some similar isomers are possible with some chelating agents. So here is the example which shows the facial and the meridional isomers. Coming to optical isomerism. When a solution of a certain complex compound is placed in the path of a plane polarized light, they rotate its plane through a certain angle which may be either right or left to it. This property of rotating the plane polarized light is called as the optical activity, and the complex possessing this property is said to be optically active. So they are said to have existing in the two following forms. One, which rotates a plane of the polarized light towards right or in the clockwise direction, said to be dextrorotatory or D form. It is also represented by placing a plus sign before the name or the formula. The second one rotates the plane of the polarized light towards left or the anticlockwise direction is called as the levorotatory or the L form, which is represented by putting a minus sign before its name or formula. The D and the L form have exactly identical physical and chemical properties, although they differ in the action of the polarized light. The D and the L forms are the mirror images to each other, just as the left and the right hand in the mirror. Third point is the isomer which is not capable of rotating the plane polarized light is called as the optically inactive. Such isomer is called as the mesoracemic or DL form. And this is an example for optical isomerism. Thank you one and all for watching this video.